Hello AP Stats students. This section of our Chapter 1 text involves changing the unit of measurement. If, for instance, we have a whole bunch of different Celsius values, for instance, and we want to change them to Fahrenheit, for instance, well, do we have to go through and change everything, or can we change those things that identify our measures of spread, or maybe our measures of center, like mean and median? And this tells you how to do it and how the data and those measures react whenever we add something to all the data or we multiply all the data by something. So in the formal definition that we have here, linear transformations, is a linear transformation changes the original variable x into the new variable x sub nu given by the equation that is found below. Okay, let me back up here a little too quick. So when we add a constant, it shifts all the values up or down by the same amount, or side to side by all the same amount. So if we can imagine that we have a set of Celsius values and we were to add 32 degrees to each one of those Celsius values, then our minimum will shift and our maximum will shift, our medium will shift, and all of our quartiles will shift. And so will our IQR, because that's Q3 minus Q1. Now multiplying by a positive constant b, that has some other effects. It doesn't move everything equally. And we'll have a good example here that maybe will demonstrate what happens. So we're looking here at the 2000 LA Lakers. Yay! All right, and the problem says that in 2000 they won the championship, and the owners of the LA Lakers gave them a choice. Said, hey, we would like to reward you guys. How about a $100,000 bonus? Now, if you look at these values, these salaries that we have here below, John Celestin, he made 0.3 million or 300,000. Well, you know what? 100,000, it looks pretty good to him because that's 30% of his salary. But to Shaq, who made 17.1 million, man, that's chump change. So he's thinking like, you know what? We can do better than that. So they went back to the owner and they said, hey, you know what? Do something better than 100,000. So the owner is like, oh yeah, Kobe, Shaq, yeah, my favorite dudes. Let's see if we can't give you a 10% increase. All right, that's 10% bonus on your salary. Well, for poor old John, 10% of 300,000, that's $30,000. So he's lost $70,000 in that deal. But Shaq and Kobe, man, they made out because 10% of their salary is pretty hefty change. So let's talk about what happens. So what you see now in this second little paragraph here, or not paragraph, but the little second box, is you see the 5-number summary from the LA Lakers salaries that they had for year 2000. So you see the John Celestin's 0.3 million, and you see Shaq 17.1 million. All right, first, do you think that 17.1 million is an outlier? I would like you to go ahead and quickly figure that out. Take that 4.5 million, which is your Q3, and subtract it your Q1, or 1 million. That's going to give you a $3.5 million IQR. Now multiply that times 1.5. I think you're going to come out with a 5.25 million right there. Now go ahead and add that on to your 4.5 million, your upper end, and that's going to give you 9.75 million. So excuse me, 5 point, yeah. So there you go. So we multiplied out there. So what happens is that both Kobe and Shaq are outliers in this particular case. So 3.5 million, so 5 points. So I think that's, yeah. Or actually, it comes out to 11 points. 9 point. Let's see, we got. Let me check it out here. I don't have a paper and I don't have a pen here, so you guys figure this out for me. So we've got 3.5 million times 1.5, which is 5.25. Yes, I was correct on that. So 9.75. So Shaq is very much an outlier in this particular case. But more than that, when we look at this this $100,000 bonus, it just picks everything up and moves at $100,000. So our minimum moves 100,000. Our Q1, our median, our Q3, and Shaq's 17.1 million, it moves 100,000 too. Okay, 100,000 also. All right, but if you're not happy with that, what happens when you multiply it? Now here we have 3 different stem and leaf plots, And first, I would like to point out that if you put a stem and leaf plot like this on one of my tests, I'm going to mark off on it because I want to know what that stem represents. So if we take a look at the far left, and let me see if I can't get my little pointer going here. My little pointer here. Where's my pointer? Get my pointer going here. What do we notice about this stem here? What is this stem? Well, that stem is our millions. So here's John Celestine's salary right there, that 0.3 million. There's a 0.7 million and a 0.8 million. And if we look all the way down here, here's the Shaq attack right here, 17.1 million. How would you describe this graph? Well, very easily noticeable is the 11.8 for Kobe and the 17.1 for Shaq. So quite clearly those are going to be some outliers, and then you see the grouping of the rest of the salaries here at the top. Now when we take and move that add $100,000 to it, so we still see that these are all grouped right in here, and we still see that Kobe, all right, is an outlier, and we see that Shaq's salary is an outlier. But the shape of that overall distribution did not change. Yeah, all the values moved up 100,000, but the shape still stayed the same. You got to remember that when we add something to the data points, the shape stays the same. Now look over here. What happens when we multiply this by 10%? Well, we still have Kobe and Shaq as outliers. They're a little more outlying on this part. All right, we still have this grouping over here. They are still there, but the shape has changed slightly. We have a fewer values in the $4 million range and one more extra value in the $5 million range. So the shape's changed slightly, but it still was recognizable to the first one. Okay. Now, when we added that 100,000, here's our 5-number summary up here at the top, and it's a 0.4 millions our minimum, and then 17.2 million is our maximum. Now suppose that when we take and multiply this by 10%, John Celestine, he's mad. He's going into the locker room. He's throwing towels everywhere. He's thinking like, you know what, man, this stinks. But you know, Shaq and Kobe, they just giving each other high fives and like, yeah, this is cool. We made out on this one. So when you look at this, though, look at down at the bottom. So this at the very bottom is the 5-number summary for the 10%, and that spread for our IQR is greater. Our spread overall is greater. It's from 0.33 million up to 18.1 million. And now I want to really reiterate here the difference between spread and range. Range is 18.81 million minus 0.33 million. That's our range. That's one number. Our spread is from 0.33 million to 18.81 million. In our problems today, you will see that they refer to spread in a slightly different way. They talk about the spread of our IQR or the spread of our standard deviation. It just means how far they are out. They're not talking about the spread of our actual data numbers. They're that 0.33 and 18.81. So please don't get the word spread confused in this particular situation. Okay, so there's our 5-number summary, and it says, look at the second paragraph down. It says that linear transformations do not change the shape of a distribution. All right, the stem and leaf plots are still heavily skewed to the right. All right, and down below we have the effects of a linear transformation. All right, we multiply each observation by a positive number b. It multiplies both the measures of the center, that's the mean and the median, and the measures of spread, the standard deviation, IQR, by that value b. And adding the number a, either positive or negative, to each observation adds measures to the measures of center and to the quartile, but it does not change the measures of the spread, which we are talking about in this situation, standard deviation or the IQR. Okay, so just so we're clear on that. All right, so now the next thing I want to talk to you guys about is the ways that we can take and do graphs of multiple sets of data. And we're just beginning to start on this, so I'll start you out really easy on this part. So the colors of cars and trucks purchased in 1998, we wanted to take and compare those. So I want you to take a look at what we have below. We have this is called a side-by-side bar chart. In some newspapers, like USA Today, we often see that these bars are stacked on top of each other. But those of us in the math world think that they're a little more difficult to analyze if the bars were stacked on top of each other, because you have to figure out where one ends and subtract it from where the other one ends. Okay, and that gives you that top bar. So it's a little more, it's not as user friendly as what we see here in this particular picture. Okay, pay attention and see how the percentage here. So if we go over and look at the full size, or intermediate, and we look at the light truck or van, what's the highest percent that you see here? I see 22%. So our vertical axis is only going to go up to 25%. Okay, so that helps you out. But look at your data first before you start graphing everything. Then you can either shade it or mark the bars with lines across to kind of let everybody know which differentiate between the two variables that we have here. And then also too, I need over here for you to put some sort of indication of what these bars represent. Okay, so that's we call it a legend in a map. Okay, now look at this particular study here. So it says a study in Switzerland examined the number of cesarean sections performed by doctors. Here's the data for 15 male doctors, and then right below it is the data for 10 female doctors. When we start looking at the spread of our data, we see here that our low number here is 20, but the high number is 85. Down here we see that the low number is 5 and the high number is 33. So we need to compare these, and when I told you guys about the biostatistics major at UC Davis, these are the kind of things that they would look at. Those biostatisticians will look at data, and they'll have to come up with conclusions that they can present to doctors and nurses and hospital administrators. And sometimes it's not very apparent, but once you take and lay it out like we see here in this stem and leaf plot, then you can come to conclusions very, very quickly. And ladies and gentlemen, this is called a back-to-back stem and leaf plot. So we take a look at this back-to-back stem and leaf plot, and the stems run right down the middle. So we have one set of stems, okay, and then we have our the data from the female doctors were on this side. So if we read this part, that's going to be 5. This will be 7. This will be 31, and this will be 33. But for the male doctors, we have to read it backwards. So this 3 represents the stem, but this is our leaf over here. So that's 31. This is 33. This number over here is 59, so you have to read it backwards. It still shows the distributions, shows outliers. We can come to some real serious conclusions very quickly by having this back-to-back stem and leaf plot, but it's just a little awkward reading it. This last number down here is 85 and 86. Okay, and those were from the data that we got from the male doctors. So this is called a back-to-back stem and leaf plot, and it's to show the distributions and help us analyze things very quickly. Okay, and that's it. Go ahead and tackle these problems. I left for the second period and sixth period, I left information on the table up front so that you guys can tackle this. This is also this PowerPoint is also on School Loop in the AP Stats Locker, and this presentation is on YouTube. I hope it goes well and enjoy.